Okay, so all right. So the number of people in attendance gives me an idea of how easy or how difficult of a time you've been having so far. So let's see. Start now. So let me just go over the topics that we have covered so far, right? So we've talked about the foundations of quantum mechanics, the mathematical foundations, the bracket, the Hilbert space structure, operators, different properties of operators, Hermitian, unitary, etc. And the measurement process, right? Properties of Hermitian operators, that eigenvalues are real and eigenstates are orthogonal and form a complete set for the Hilbert space for any Hermitian operator. So this is all, like, I mean, the basics, right? The beginning. So if you, so now, yeah, so before I go on, if you, first of all, so you have to ask me the questions, okay? Like, I don't know what it is exactly that you might have doubts about, so you have to ask me questions. Okay, so anyway, so I'll continue. So the mathematical foundation, right? And then we have talked about. So now let me go back a little bit to my notes, so I'll remember what all we've talked about, right? So we've talked about different systems, different examples of say quantum systems, right? So let's see. And yeah, so after the mathematical foundations of quantum mechanics, then what's the next step? The next step is to understand how do you describe time evolution, right? How do you describe the evolution of a system? So that evolution is described in terms of what is called a Hamiltonian, which also has to be a Hermitian operator, right? And this Hamiltonian, so let's see. Excuse me just 1 minute, okay? Okay, yeah. So let's see. So then we have this notion of time evolution. So okay, let me just 1 second. So put this on do not disturb. Good. So I'll just write down all of these right? So one is the mathematical preliminaries, right? Vector spaces, operators on vector spaces. Hermitian unitary, etc. Then properties of various kinds of operators. Okay. Then there are some other properties of vectors. One important property is that of completeness. This is a very important property that you should know, and you should be able to work with it, right? Completeness means that if I take any set of basis vectors, then that set of basis vectors can be used to form a operator which is the identity. So for this, the other important concept that is being used is that of outer product, right? So you're using the outer product. So you start from a vector, right? You have vector phi. You take the outer product of the vector phi with itself. This is the outer product, right? And what is this? This guy is an operator. So, and then if you take sum over I of a complete set of states, then what does this become? This becomes an operator, the identity operator, right? So this operation, what is going on here? Taking and of course, in general, you can take any two states. So they don't have to be the same, obviously, right? And take the outer product. Of these two states like this. And what is this? This is an operator, right? So this is something that you can do in ordinary linear algebra. This is not something that is special to quantum mechanics, right? This is just the outer product. If you take the outer product of any two vectors, you get an operator, right? So then you have the notion of this thing, composite systems. Composite systems. So for this, you need this concept of a tensor product, right? So the tensor product is similar to, but not identical to the outer product, right? So if you have two states, phi and psi, then the tensor product is written in terms of this symbol, a cross symbol with a circle, right? And what is this? This is the tensor product of these two. And what is it? This is also a state now, right? So if you then properties of the tensor product of a Hilbert space. So for example, if I take two Hilbert spaces, HA and HB, then if you take the tensor product, right, you get a bigger Hilbert space, HAHP, and the dimension of this bigger Hilbert space is equal to the product of the dimensions of the constituent Hilbert space, right? So you have all these. This is the mathematical, these are the mathematical tools that we use in describing quantum systems. There are other things that I have not talked about. They are known as density matrices, which are very important, and some other kinds of maps. But you know, for our purposes, these are enough. Then the second thing is, you know, what are the quantum? What is a? So I'll call them the quantum axioms. Right. So the axioms of quantum mechanics. What are the assumptions of quantum mechanics? Right. So you have that every system can be described by a state. Then the time evolution of or the dynamics, right? So what is all of this? This mathematical foundation, right? All of this, what is this? This is one way to describe this is that this is kinematics. Kinematics means how you describe the system, the state of a system. And then what comes after kinematics? After kinematics, you have dynamics. Right. So the dynamics describes how systems evolve in time, how they interact. So you have time evolution. So time evolution is given by in terms of some unitary operator, right? And why is it given in terms of a unitary operator? So that, because if that is not the case, then probabilities will not be conserved, right? So that means basically that if you don't have a unitary time evolution, then a vector which is of length unit 1 will not remain of length unit 1, right? So we have this requirement that so when we say a vector is of length unit 1, what does that mean? That means that basically the sum of probabilities of finding any component of that vector, right? That sum is equal to 1. So if the length of the vector is not 1, then that means that, you know, we don't know how, we have either missing probabilities or extra probabilities, and we don't know what to do with that, right? So either a system is losing information or gaining information. So there is a way to describe such systems also. But if you have a closed system which is not losing any information or gaining any information, right? In that case, your evolution has to be unitary. So you have these quantum axioms, you have this time evolution, and then you have physical observables. Physical observables are given by Hermitian operators, right? Why? Because Hermitian operators have real eigenvalues, right? And the reason we want real eigenvalues is because, well, the results of our measurements are real numbers. Okay, that's the common traditionally accepted explanation. Though one can maybe argue or debate about this. So then we have the dynamics is described by then this unitary operator. It satisfies the in fact, this equation is true for any operator, right? So instead of unitary operator, one can put in any operator, right? This is just the time evolution of an operator in the Heisenberg representation. So if you apply it to unitary operators in particular, this is one. Then from this, from applying this to unitary operators, what one finds is the Schrodinger equation comes out of this. Right? And what is the Schrodinger equation? It is a statement that h of acting on psi of some t is equal to I h bar d by t psi. So this is the basic equation of quantum mechanics, right? This is the Newton's law of quantum mechanics, Newton's second law, right? And now the thing is that, well, all systems. So this talks about time dependent states, right? So what happens if a system? So what is this? First of all, I h bar d by dt. This thing is, what is this? This is an operator, right? And this corresponds to the energy of the whole system, right? Because the Hamiltonian is also measures the energy of the system. So you can write the Schrodinger equation as this eigenvalue equation also. Okay. So now H is an operator, psi is a state, but this E is an eigenvalue. Okay. So if you work in a basis, if you work in a basis in which you are so this is a Hermitian operator, and if you work in the basis in which this operator is diagonal, basically meaning that the eigenstates are the eigenstates of this basis states are the eigenstates of this operator, then your Schrodinger equation can be written in a way that becomes time independent. So the so these, now this state doesn't depend on time. Okay, and the thing is, this has to do with ultimately where does this come from? This comes from the measurement axiom, right? So what is the measurement axiom? Measurement axiom says that you perform a measurement on a system by using an operator, right? Hermitian operator. And what happens after measurement is that, let's say you have some so your Hermitian operator is physical observable. Okay, and the set of eigenstates So let's say O is your Hermitian operator. So then any state can be written as a sum of this eigenstates of this Hermitian operator. So what is the C of I? This is just the coefficient of this vector in this spaces. And what is the lambda of I? These are the eigenvalues. Right? So what happens when we perform a measurement of this, when the system is in a certain state psi and you use this operator O? Well, when you have measurement, then means that you have a collapse. So what is the meaning of collapse? Collapse means that basically your system psi, your state of the system is psi, right? It's some superposition of these eigenstates. After measurement, the system collapses into some particular eigenstate, phi of k, right? And with a certain probability, that probability is determined by the coefficient of this state. So this is the probability of the system ending up in this state, phi of k, right? So, yeah. So if you are in an eigenstate to begin with, then after measurement, what will happen? You will remain in that eigenstate, right? So if you measure eigenstate of your, and then if your Hermitian operator happens to be the Hamiltonian, right? What will happen? And you are in an eigenstate of the Hamiltonian, you will remain in that eigenstate, and the system will not, there is no time evolution of that eigenstate, right? So these states are called stationary states, right? So eigenstates of Hamiltonian or of the energy operator are stationary, right? They don't evolve with time. So this is these are the quantum axioms, right? And then we have not really discussed how to apply these quantum axioms to composite systems. You know, maybe we'll do that at some point. So then the next thing, so this is a continuation of this is the dynamic. This is the dynamics. Okay. Am I missing anything? Probably I'm missing many. Doesn't matter. This is the basic set of requirements you need. Okay. Okay. Then number 3. So we come to actual examples, right? Examples of quantum systems. So the first example is just the free particles. Well, the simplest example is that of a spin 1.5 particle. Right, and for this, here what you have is you have a certain Hilbert space H, whose dimension is 2. So this is the simplest possible Hilbert space, right? And so this is a simplest possible quantum system. This is like when we talk about classical mechanics, we talk about a point particle, and we talk about a 3-point particle. That's the simplest classical system. So in quantum mechanics, this is our simplest quantum system is a spin 1/2 particle, which has a Hilbert space dimension of 2. And so there are 2 possible states, up and down, or 0, 1, right? And all operators are basically just 2 by 2 matrices, right? Then in this system, what you have is you have all operators are two by two matrices, right? So all of the linear algebra becomes simple. So you have certain operators such as the Pauli matrices. So these operators are important to remember the expressions of these operators. And then these Pauli matrices have certain commutation relations. So sigma I, sigma j is equal to 2I epsilon I j k. This I is the imaginary number, and this epsilon I j k means this is the completely so if this thing permutation of these indices ijk is an even permutation, then it's +1. If permutation of ijk is an odd permutation, and then if it's not a permutation, that means if any two of the indices are equal, then this guy is equal to 0. So maybe I didn't mention this operator in class, but this well, it is but this is how you can write down this expression. Okay, just 1 second. Right. Then the next possible system is a free particle. Now, a free particle has an infinite dimensional Hilbert space, right? So your state psi is written as some superposition of, let's say, a set of eigenstates which are called position eigenstates. And if you have since you have an infinite number of eigenstates, you have one eigenstate for each point on the real line. It is an infinite dimensional Hilbert space. So suddenly we have gone from 2-dimensional Hilbert space to infinite dimensional Hilbert space. It seems like a massive jump. But I mean, the tools are all still the same, right? We are still dealing with vectors. We are still working with superpositions of different vectors. The only thing is that instead of sum everywhere, you have an integral. Then So for such systems, you can write down the Schrodinger, the Hamiltonian can be written as a differential operator. So the Hamiltonian becomes this guy minus h bar square by 2m del square plus v of xt, and this is your Hamiltonian. So if in case you have a time dependent potential, that's why I put a t. It doesn't have to be a time dependent potential. So the Schrodinger equation becomes h psi, and instead of writing in terms of the ket psi, I can just work in terms of the components of psi. So I can just write h in terms of psi of x minus h bar square 2m del square psi, and again this can be time dependent, so I'll put that here. So this is the Hamiltonian operator acting on the state psi, and the Schrodinger equation then tells us that this is equal to d by dt of psi of xt. Okay, so it's a little bit small. I hope it's visible. Okay, so I'll pause here and ask for any questions up till this point before I continue for the next part of the discussion. Questions? No questions? Okay. So see, because I mean, I can work through examples, but I don't know which examples to work through unless you tell me, you know, that you have a difficulty in understanding so and so problem from so and so homework set. Otherwise, I don't know what to do, because there are lots and lots of problems, right? So you can just stop me at any point and ask me a question if you think of it. Okay. Are people still there? Are you all listening? Anybody's there? Everybody's.
Yes, sir.
Okay.
Yes.
So the thing is that, see, there is a conceptual jump in going from infinite dimensional from finite dimensional Hilbert space to infinite dimensional Hilbert space, and that conceptual jump is a little bit tricky. It takes a little bit getting used to. Okay. So you have to remind yourself that this thing. Going from finite dimension to infinite dimension, right? So what happens when you go from finite dimension to infinite dimension? So you have, let's make it a table, finite dimension, infinite dimension. Let's make nice lines. So in a finite dimensional Hilbert space, right, you have a discrete index, because you will I is equal to 1 to till n. And in infinite dimensional Hilbert space, you can have both discrete indices and continuous indices. So you can have a discrete index also, to n, where n goes to infinity, right? Or you can have a continuous index. So instead of writing psi of I, what you do if you have a continuous index is you write psi of x, where x belongs to, let's say, the real length. So to write this a little bit differently, you write psi of I, where I belongs to 1 to n. Here you have psi of I, where I belongs to 1 to till infinity. Right? So then what else? So when you take inner products of states, for example, so when you take some psi, so if you want to write down an arbitrary state, how would you write it? You would write it as a superposition of some set of basis states, and you would write it as a sum. But in this case, right, you have two options. One is that you write it as a sum when n is infinite. So then in the discrete case, it's just the same thing. But in the continuous case, it is written as an integral, right? So an integral is this is the basic idea behind calculus, right? In general, that calculus is about taking a sum basically, but then the sum becomes a sum over some continuous variable, and when you do that, then you take some limits and all, and you get your sum becomes an integral, right? And there is a slight shift in notation, which is a little confusing to people, which is understandable, which is that in the discrete case, in the continuous case, we write the coefficient of the state in this way, psi of x. And so what happens is that in most quantum textbooks, they only work with this Schrodinger equation, this type of Schrodinger equation for a continuous system, right? Spin 1/2 systems are discussed at the end, or they are not discussed at all. So then when you write down this psi of x in this way, so the coefficient is, this is called the state, right? Psi of x is called the state, right? But technically it's not, right? Technically, what is the state? The state is the full state. This is a component. So of course, one could apply the same terminology here also. Instead of writing C of I, right, one can write psi of I. Okay, but I mean, we don't live in an ideal world where everything has been made consistent, unfortunately. Okay, so then what else? Then, so for example, when you take something like an inner product, so inner products. So if you take the inner product of two states, let's say you have two states, psi is equal to some phi I, and then you have some other state psi prime, then I can write that as C prime phi I, right? It's the same, you're using the same basis, right? Then if you take the inner product of psi and psi prime, what do you get? You get a sum over I of Ci star Ci prime. Right? So when I take this bra, this Ci becomes a complex conjugate, right? And this is if these eigenstates, we are assuming that these states are orthogonal, right? So how do we write this orthogonality? We write it in terms of this. This is the Kronecker delta. Right? For continuous for systems which are infinite dimensional, right? Again, you have two cases. One is the discrete continuous case, and in that case, everything remains the same. Your all of these expressions remain the same. The only difference is that I just becomes a, instead of going from 1 to some finite number, it goes from 1 to infinity, and your Kronecker delta becomes some infinite dimensional matrix. Not infinite dimensional, sorry. Well, yeah, infinite dimensional, right? So all the number of rows and columns are infinite. So for the discrete case, it is same only with n going to infinity, right? So it is in the continuous case that you get a difference. In the continuous case, now if you want to write down a state, right, you write it as an integral. So if you have two different states, let's say psi, so I'll write it as psi of x, x dx, and then I have some other state phi, so I would write it as something like this. Okay, and now when I take the inner product of these two states, so phi and psi, right, what is the answer? So the answer is that phi star x psi x dx, right? How do we get this expression? We get this expression by just taking the bra of this and taking the ket of this and multiplying those two together, contracting them. But when you do that, you have to remember to use a different index. Remember, this x is an index. So the same way that when you do if in the continuous case you were to do this psi prime, how would you do it? You would first write down psi and you would use an index I, let's say. So you would write down the bra of psi, which is Ci star, and then bra of phi, right? And then this guy multiplied by psi prime. Now psi prime you would write as sum over a different index, right? Because this I index is already taken up. You can't use this I index again. So you have a different index. You would write it as j, and then you would write this as Cj prime, and then phi j, like this. So then this would become sum over ij Ci star Cj prime, then the inner product of phi I and phi j. Right? Then this phi ij, we put this delta ij, and it becomes sum over I Ci star Ci prime. So in this, so the same, it's exactly the same thing in the continuous case. Right? In the continuous case, what do you have? You have this phi bra. So what is the bra of phi? Sorry, the bra of phi is just the bra of this guy, which becomes the integral. Remember, is just a sum over the index. And then taking the bra of all of these quantities, what do you get? You get psi star x, right? That's how you take the bra state. Then the ket becomes the bra and you get dx, right? And then what about the phi state? The phi state now becomes phi of x prime. This is where people get confused very often. So instead of x prime, let me use something else. Let me use y. I'll call it phi of y, and then y dy, like this. This is just an index, right? Remember, so I can call it anything I want. So now this whole thing becomes a double integral. Just like this becomes a double sum, this becomes a double integral, right? Psi star x, phi y, then inner product of x and y, right? This inner product, now this is right where the next difference comes, is that this becomes a Dirac delta function. So this becomes a, instead of a Kronecker delta, this is a Dirac delta, we call it, right? And then using this Dirac delta, you are left with one integral, which is psi of x and phi of x. Yeah, sorry, I should be consistent here. This is psi phi. So I'm changing this instead of changing everything over here. Okay, so right. So this is the thing, is that in the continuous case and the discrete case. What else? So in the, we can write down tensor products also the same way. So let's say, for example, you have two free particles. Okay, so two free particles on the real line. How would you write down the state of the whole system? So you would write down the state of the first particle, let's say as psi 1, right? Or you can write psi of A for the first particle. What would this be? This would be psi of AX, ket x, dx. Then you have the second particle. It would have this kind of an expression, right? So now this psi of A and psi of B, these are different functions of x, right? Then how would you write down the composite system, psi AB? It would be psi of A tensor with psi of B, right? And then what is that? Well, it would be this guy tensored with this guy. So when you do that tensor product, what do you get? You get a double integral again. You get psi AX, psi B, let's say Y. Then X tensor with Y, integral over dx dy. Right? So this looks like a very complicated expression. But ultimately you see that, well, the product state is simply this thing, right? Its coefficients are simply the products of the coefficients of the original two states. Anyways, this is just an example, okay? Then after all of this, what we have is we have free particle. So we have so what are all the systems that we have talked about? One is a spin 1/2. Then we have a particle on a real line. It can be free or not. Particle on one line, so in 1D. So then we can have different potentials with potential, right? So then the potential can be, and this is now a static potential. It doesn't have any time dependence. So it can be 0. So you have a free particle, right? Or non-zero, right? Then this V0, it doesn't need to be a constant, right? So one example of a non-constant potential is the harmonic oscillator potential. So this is your simple harmonic oscillator, right? So for the harmonic oscillator, we have this, we can write down the Hamiltonian of the harmonic oscillator as p square by 2m plus 1/2 kx squared, right? Operator, operator, operator. And then what happens? How do we have a certain trick, right? What is that trick? This can be written as some quantity A whole squared plus some quantity B whole squared. And this whole thing can be written as A plus B. So A plus, sorry,
A plus iota B.
Right. A minus iota B, right? But now these are operators, right? So you have to add a commutator term here to cancel out the commutator which comes from the product. So in this case, what is the commutator of P and X now? P and X, the commutator of P and X is equal to IH bar. So what happens to this term? This term just becomes a constant. And
minus
so
IH cut.
Sorry?
Minus IH cut, sir. PX.
ठीक है भैया, minus IH. H bar बोलते हैं, H cut नहीं बोलते हैं. मतलब you can call it H cut if you want. But what is the, so H bar is this, so then H bar becomes this guy, H bar omega A dagger A plus 1/2, right? So what is this A dagger A? This is this product, and where is this 1/2? It comes from this commutator. Then we look at the commutation relations of all of these different operators with each other. So if you have this Hamiltonian, and now I'll just drop the hats, okay? No more hats. I don't need those. So if you look with H with A dagger, you get A dagger. If you look at H with A, you get minus A. And if you look at A with A dagger, you get 1, right? This just comes from the commutation, the standard commutation relation of momentum and position. Then using these properties, we can construct the set of states. So, right, what we find is that if you take A dagger and if you have a set of eigenstates of H, so they are labeled by some parameter n. Okay, we don't know what n is. It's some arbitrary parameter. It can be continuous, real, it doesn't matter. And then what we find using these commutation relations, what we find is that when you take A dagger and act on n, then you get n plus 1. Again, we don't know whether n is real or not, whether n is a integer number or what it is, right? It's just some label. And similarly, when we take A on n, this gives us something proportional to n minus 1, right? So then if we say that H has some ground state, right? So H has some ground state. So that means there is no state below this, right? So this ground state then A or acting on 0 is 0, right? And then from this procedure, we can also deduce that n is actually a positive, well, it's a whole number. So how do I write whole numbers? It's a positive integer and 0. It can also be 0, right? Okay, so then you have these properties of A dagger and all that. And what is the interpretation of n? N is the excitation level of the system. Now this is all in this is called the Dirac procedure, right? One can also look at the Schrodinger equation and solve the Schrodinger equation for this. So this is the energy basis. And for the Schrodinger equation, we can also, we would use the position basis. So the same state, psi, can be written in the position basis in this way, or it can be written in the energy basis in this way. Okay. So this is another example of a relation between a discrete and continuous representation. So this is a state. When you write it in the energy basis, it has a discrete representation. When you write it in the position basis, it has a continuous representation. Right. And when you work in this position basis, you can solve for these this eigenstates. You can solve for this psi of x by putting into the Schrodinger equation, right? So you get this Schrodinger equation. Right, and this is for the time independent. This is the time independent Schrodinger equation, right? And so when you solve this, what do you get? You get that psi of x is given by some normalization factor, okay, times some this thing, something which is called a Hermitian polynomial, Hermite polynomial, and then these states are labeled by some index n. So Hermite polynomials are labeled by n. Right? But then it turns out that this n is just this same as the energy eigenstates. Right? Then there is a correspondence between the Hermite polynomial and this number operator eigenstates, but we haven't looked at all that, right? So this is harmonic oscillator. Then we have coherent states. So I'll do one thing. I'll leave coherent states out of the Midsem for you. Okay. I think that will make everybody happy.
Yes, sir.
Yes,
डर
sir.
लगता है
Thank
ना?
you.
डर लगता है ना सोच के कोहेरेंट स्टेट के बारे में? तो ठीक है, मैंने छोड़ दिया. खुश रहो.
धन्यवाद, sir.
हाँ, ठीक है ना. मतलब when I look at all this material, I'm like, yeah, this is enough for Midsem, right? कितने पेज हो गए? 4 पेज का मटेरियल तो हो ही गया. और that is all just a summary. काफी, it's a lot, right, when you think about it. ठीक है ना? So free
जी, sir.
particle and harmonic oscillator, this thing you should know really well. And then what else? Very important, uncertainty principle, right? You should remember the uncertainty principle. There's a general statement of the uncertainty principle, right? What is the general statement? That if you have two operators A, B, which don't commute with each other, then if you take the product of the, so you can define the uncertainty in an operator. What is the definition of the uncertainty in of an operator? It is the square root of this thing, right? A square, expectation value of A square minus square of the expectation value of A, right? And so then you have this is a general identity, right? This is equal to the absolute value of the expectation value of the commutator of A and B whole square. This is the general statement of the uncertainty principle. When you put momentum and position instead of A and B, you get the statement that you are familiar with, which is that delta x times delta p is equal to h bar by 2, right? And what is x and p commutator is IH bar. So IH bar I guess there should be a factor of 1 by 2 h bar here, something like that. I think I'm missing something. इसको आप लोग check कर लिया ना? Because of course you should, when you study for the midsem, right, you have to actually open your textbooks. So sorry to make you do that, make that effort. I hope it is not too painful. Okay. No, sorry, this there is no h bar here. यहाँ पे नहीं है. So मैं थोड़ा कंफ्यूज हो रहा हूँ, but it's okay. You go and look it up, okay? So this is the uncertainty principle. Then uncertainty principle can be applied to all kinds of operators. You have to remember this. A and B can be any operators. It can be annihilation operator, creation operator, so on and so forth. Then this uncertainty is being measured in some state, right? We are taking expectation value. It means expectation value is taken in some state, right? So we are not specified what that state is. So that state can be anything. It can be a number operator eigenstate. It can be some superposition of number operator eigenstate. Okay.
Sir, the square is not coming of the absolute value of the commutator.
Oh, square is not there, no?
Yes, sir.
Square is not there. Right. That fixes the problem. Thank you. So coherent states is not in Midsem, and I guess RNFS theorem also I'll leave out on Midsem. Okay. So I think this is enough. Okay. Because I mean, I've covered many of these topics in the homework problems also. All right. Now I have to do a lot of corrections, and there's the quiz that's still pending. Midsem will come on Monday. Then your homework sets are still pending. Actually, I don't have any assistants now. I don't have a teaching assistant. Normally in a course like this, I should have a teaching assistant, but I don't. So, some of the work, it takes a while to get it complete. Okay. Now people have not really asked me questions, so I don't know what more to say. Chinmay is also very happy. Yes, no coherence states. So please ask me if you have any questions. Otherwise, you go and just revise the homework problems, revise the quiz, work out the quiz problems. All right. Supposed to my internet connection sometimes it disconnects, so got disconnected there for a second. So are there any questions? Sudeep, Varun, Pranav,
No,
are you
sir.
guys still there? Huh? Okay, so if there are no questions, then I guess I'll end it here. You can ask questions on the Telegram group or on Moodle. Okay. And otherwise, I'll see you on Monday. Funny. All right. So I hope this is useful. Okay.
तो पैटर्न सेम रहेगा ना वो क्विज जैसे आपने लिया
पैटर्न मतलब हाँ लॉन्ग आंसर है
ओके
राइट long answer meaning that I don't really ask you to write long answers. I mean, some answers I can ask you, which you should know. Also, you should remember the history of quantum mechanics, the basic history. Okay, that also part I forgot to mention. Things like Stern-Gerlach experiment, black body radiation, ये सब चीजें आपको थोड़ा you should know photoelectric effects, क्या चीजें थी. Okay, what are the things that led to the development of quantum mechanics? Okay. All right. So I guess I'll end it here.